Okay, this is kind of, again, these are just sort of typical related rates of change problems. I'm going to keep the numbers nice and convivial. A 10-foot ladder slides down a vertical wall at 2 feet per second. 2 feet. We'll stick with that, 2 feet per second. All right? Now, this is an amazingly simple problem. It's easy to write. And I'm going to do A. How fast is the ladder moving, there's a G in there, away from the wall when the top is 6 feet from the ground. Okay? That's part one. Part B is, like I said, real standard issue problem. How fast is the area? How fast is the area of the triangle made by the ladder and the wall and the wall changing at the same time as part one, same time as in part A. I guess it's A and not 1. Okay, so first things first, you ready? We got a 10-foot ladder. Now, ask yourself a question. Is it changing or isn't it? Is the length of the ladder changing? So do you see what's going on here? The ladder is sliding down the wall, right? It's sliding down the wall at 2 feet per second. Well, at the same time, I mean, assuming that the ladder's not bending and it's not bouncing around, it's sliding away from the wall as well. All right, so let's label what we got here. But probably the most important thing that you see first, and because this sort of this is a theme that sort of rings through these problems as you work through them, excuse me, is what kind of a triangle do you see here? It's a right triangle. As soon as I see a right triangle, my spidey sense starts to tingle. I start thinking to myself, hey, I'll bet Pythagoras comes into play here. Now, you ready? First things first. When do we take the snapshot? When was the snapshot taken? Well, the snapshot was taken when this was 6. Well, let's label this. How about when y equals 6? All right? Now, let's see. It's a right triangle. This is 6. I'm going to label this side x. Let's see. Last I checked, x squared plus y squared equals z squared. So I need x, don't I? So x squared plus 36 equals 100. It looks like x squared equals 64, so x equals 8. Cool. I got a piece of information I could throw in there. Now again, ask yourself this question. Are x and y changing as the ladder slides down and away from the wall? Hopefully you see that the answer is yes. Okay? All right, what else can we label? I'm going to change colors. What else can we label? Well, I know for sure if the ladder is sliding down the wall at 2 feet per second, that's dy over dt, isn't it? So I know that I'm just labeling stuff, just throwing it on here. I know this is dy over dt is 2 feet. Now wait a sec. Is it 2 feet though? It isn't. It's shrinking. So the direction, whether it's growing or shrinking, is really important, and we need to respect that negative because dy over dt is negative because y is shrinking. Okay, so now remember that whole dialogue that I have with myself? What am I looking for? How fast is the ladder moving away from the wall when, look at this, it's like karaoke, when the top is 6 feet from the, okay, so what am I looking for? I'm looking for this guy right here. Well, what is that? That's dx over dt, right? That better be positive because x is growing. So what I need is a formula that's got an x in it. Gosh, if only I had a formula that had an hey, look at that! Pythagorean's theorem has an x in it. Okay, so let's write this thing up. X squared plus y squared equals z squared. Now notice I had to do quite a bit of dirt work here. This is all dirt work that I had to use to set up my problem. All right? So let's look at this. What about this equation is changing vis-a-vis this problem, and what isn't? Because if it's not changing, it's a free piece of information. You get to throw that piece into the equation, which makes it really useful. Well, the ladder, this is z. Z doesn't change. The length of the ladder doesn't change. So I get a free piece of information. X squared plus y squared equals 10 squared, affectionately known as 100. I have taken this as far as I possibly can. Remember, I'm looking for dx over dt. I have an x, a y, and a constant, so I'm going to differentiate this using implicit differentiation as though I'm differentiating a function of t. Well, the derivative of x squared is 2x, but I treated it as though it was a t, so I need to leave a footnote, plus 2y dy over dt, and that equals 0. I'm going to solve for dx over dt, right? So, in a puff of algebra, I end up with 2x dx over dt equals negative 2y dy over dt. I'm simple country folk, so I'm going to cross off these two guys, and that leads me to dx over dt is equal to negative y over x, I just divided through by the x, right, times dy over dt. I need an x, check. I need a y, check. And I need a dy over dt to be able to solve this problem. So dx, should use my implication arrows, dx over dt is equal to, now one thing at a time, negative y, which is negative 6 over 8 times dy over dt, which is negative 2. Now let's insert our units real quick. Okay, I'll do these in red. Just to make sure that when we're done, we better get feet per second, right? Okay, so 6, that's feet. 8 is feet. Oh, that's nice. These guys cancel out. And 2 was feet per second. Isn't that nice? Our negatives cancel. I end up with feet per second, which is what I want, right? Excuse me. I apologize. What do I end up with? 3, 6, so 1.5, right? Is that right? Yeah, I do. So positive 1.5 feet per second. Now you notice I'm getting kind of lazy with my fraction bars. I should pick a way and stick with it. I typically don't like to slant my fraction bars because I might confuse stuff in the denominator from time to time. Ta-da! Ooh, now let's do B. How fast is the area of the triangle made by the ladder and the wall changing? The area. So this is part A, and let's talk about part B. Now, what am I looking for? Well, this is the triangle. I'm looking for dA over dt. Now, I want to show you something that's really important here. If you don't fight this, if you let yourself ask the correct questions to yourself, it'll almost do the problem for you. Look, I'm looking for dA over dt. What does that imply? It implies I need an A. The area of what? The triangle. Well, what's the area of a triangle? It's 1/2 the base times the height, right? Which in this case, my base is x and my height is y. So I get 1/2 x times y. True? Well, that's kind of cool. So I've got area equals 1/2 xy. I need a dA over dt, so I'm going to differentiate this with respect to time. Now watch what happens. The derivative of A is 1, and it leaves behind a dA over dt. Phew, thank God. Now this one's going to get a little tricky because I got a product in here. So I'm going to look at 1/2 x as one part of the product, and y as the other part of the product. So I get 1/2 the derivative of the first, right? So the derivative of x is 1. There's the 1/2 that's along for the ride. That's the constant part, right? So I'm going to end up with 1/2 y, but remember I differentiated x with respect to t, so I got dx over dt plus the derivative of the second, which is 1 times 1/2 x. So I end up with 1/2 x times 1, but I have to remember leave a dy over dt. Now, this is what I'm trying to solve for. Let's see if we can grab everything that we need. 1/2, that's easy, that's constant. Y, check. Dx over dt, check, I just solved for it, right? And then x, check, I solved for that earlier, and dy over dt, that was given. So look at what we get. I get 1/2, y is 6. Now, I'm going to do this again. Let's make sure, because remember, we're looking for a change in area. So what should my units be? Should be square feet per second. My dx over dt from the problem before, I'm not going to do decimals and fractions because that's just blah. So I'm going to leave that as 3/2. This is going to be 3/2 feet per second, right? Plus 1/2 times x, which is 8 feet, times dy over dt, which was given, right? That's a -2 feet per second. Respect that negative, man. It happens so often that students will screw that up. I'm going to move my equal sign over here. I hope nobody is offended. So let's see what we get here. What do I end up with? 2 goes into 6 3 times. Looks like I get 9/2 square feet per second plus, let's see, that 2 and that's, so plus what, -8 square feet per second. That's cool. -8 feet per second. And let's see, last I checked, 9 minus 16, 16 halves, right? So 9 halves minus 16 halves, finding a common denominator, is going to give me what? -7/2 feet squared per second. Which, if you think about it, now, as this thing slides down, the area, let me get us a new page, because that's just ridiculous. So look, I'm sure that there's an applet or something that I can find on a website. So this is my wall, all right? Look, if my ladder's right there, so this is my 10-foot ladder, right? And this thing starts to slide down, and this thing starts to slide out. Well, let's take a later snapshot. So I've got my 10, and now I'm here. Well, what's happening to my area? Here's my area 1, here's my area 2. It's growing, right? But as this thing slides down some more, and this thing slides away some more, watch what happens. Here's my wall, here's my ladder. It's starting to shrink again. So as the ladder slides down the wall, the area, as long as the ladder's quite a ways up, the area grows, and then it shrinks again. We just happen to catch it at the point past the halfway point at which it starts to shrink again, which was right here. Right? Isn't that fun? It's a great time. It's really, really cool. Now, I will tell you this. 9 times out of 10, Pythagorean's theorem can be used to solve a related rates of change problem. 9 times out of 10, that's the case. But even if it isn't, you don't panic. You just look at what, probably the most important question that you can ask yourself is, what rate of change am I looking for? Oh, in this case, it was area. So I need to start with an area. Ooh, let's go back to I'll go back to my red pen. I'm sorry, my green pen. Let's go back to green. Notice I didn't get to plug in any values into this guy because everything was changing. Area was changing, x was changing, y was changing. They were all changing. So unlike here where I got to throw in the 100 because the length of the ladder never changed, we don't have the length of the ladder in this equation for the area of the triangle. So we were always stuck. All right, the only constant that was along for the ride was the 1/2. Okay? All right, that's a brief introduction into related rates of change. We are going to do a boatload of these. You'll get very good at them, I promise. We're going to spend a few days on, or a couple days, not a few, but a couple days on this, just playing. So I will see you in class tomorrow. Hope you enjoyed. Have a great day. Bye.